Good day everyone, I am Rose Ansi Manzanal, a third-year geological engineering student of Batangas State University. Today, I will be presenting a study entitled Unraveling the Dynamics and Hazards of June 3, 2018 Pyroclastic Density Currents at Fuego Volcano or Guatemala. On June 3, 2018, Guatemala's Fuego Volcano erupted, sending pyroclastic density currents, fast-burning clouds of gas and ash, racing down its slopes. These currents overwhelmed the village of San Miguel de los Lotes and traveled more than 12 kilometers from the summit, killing hundreds. This event shocked scientists and exposed how unpredictable small-volume PDCs can be. To better understand this tragedy and improve future hazards assessments, researchers carried out a detailed, multi-pronged study, and they analyzed everything from grain sizes and ash textures to satellite imagery and terrain models. Their goal? To uncover how these flows formed, move, and ultimately cause such devastation. Small volume pyroclastic density currents may sound less threatening than massive eruptions, but they are among the deadliest volcanic hazards, and these flows made of hot gas and volcanic particles can move at over 100 kilometers per hour and travel several kilometers downslope. They have two-layer structure, a dense, concentrated bottom layer and a lighter ash cloud surge riding above. While usually confined to deep valleys, things get dangerous when they overspill, scaling the valley and sweeping over nearby terrain. This overspill or overbank flow is often what causes the most destruction and deaths. These events are hard to predict because they depend on subtle changes in the terrain and internal flow conditions. That is why understanding how PDCs interact with the landscape is critical for improving volcanic hazards assessment. Fuego Volcano, standing at 3,763 meters, is one of the most active volcanoes in Central America. After centuries of activity, it reawakened in 1999 and has been erupting frequently ever since, with ash-rich explosions and sudden violent bursts, known as paroxysms. On June 3, 2018, Fuego unleashed one of its deadliest eruptions. It began with early morning seismic activity and small explosions. But by 1:10 p.m., it had evolved into a powerful subplinian eruption, sending a plume up to 19 kilometers high. To understand how the pyroclastic flows behave during the 2018 Fuego eruption, researchers launched two major field campaigns, one in August 2018 and another in January 2019. Their primary focus was Las Lajas ravine, the area hit hardest by the flows. They also gathered samples from the Ceniza and Seca ravines, though many areas had already been disturbed by rain-triggered lahars. Using tools like GPS units, drones, and satellite imagery, they mapped out the deposits and measured how thick the pyroclastic layers were, sometimes using a laser rangefinder, other times using a high-resolution elevation model taken just one day after the eruption. In total, 34 samples were collected. These were analyzed in labs to study grain size distribution and rock types. The researchers used sieving techniques and specialized software to break down complex particle size patterns. They also analyzed textures and surfaces of individual ash particles under microscopes, including a scanning electron microscope, which gave them high-resolution views of the volcanic fragments. After the eruption, researchers used satellite image and on-the-ground surveys to map the deposits left behind by the pyroclastic density currents. They identified three main types of deposits. First, thick valley confined flows that stayed in the channels. Second, overbank flows where materials spilled out and swept across slopes. And third, ash cloud surges which were thinner but traveled further. To understand how the pyroclastic density currents behave, researchers dug into their internal structure. They identified 5 main lithophases or deposit types, based on characteristics like grain size, layering, and composition. The valley-confined deposits were thick, sometimes over 20 meters, and filled with large boulders. These layers often showed a aligned clast and color changes caused by oxidation, giving clues about the sequence of flows, with later ones being more oxidized. In contrast, the overbank deposits form when flows is filled out of the main channels. Some created wedge-shaped layers near the valley walls, while others were redirected into smaller tributaries. These were typically less sorted but still carried large blocks. They also found ash cloud surge deposits, which were layered and sometimes showed small dune-shaped structures. These lighter, more distant deposits often left thin ash layers and scorched vegetation, helping trace the timing and extent of the surges. By analyzing these deposits and their structures, scientists were able to link specific flows to specific areas of destruction, like the overbank units that buried San Miguel de los Lotes. To understand how the pyroclastic flows behave and evolve, scientists analyzed the grain size and composition of 30 samples from different parts of the June 8, 2018 deposits. Most samples had bimodal grain size distributions, meaning there were two dominant particle sizes, one coarse and one fine. Valley confined and overbank deposits shared similar characteristics, mostly poorly sorted, with fine ash making up around 20 to 25% of the material. Ash cloud surge deposits, in contrast, were finer and more evenly sorted. When looking at what the matrix was made of, it was called componentry. The dominant components were free crystals, oxidized clast, and black scoria. A clear pattern emerged. Farther from the summit, there was an increase in black scoria and a decrease in hydrothermally altered and oxidized clast. This tells us that as the flows traveled, they evolved both in particle size and material makeup, likely due to internal dynamics of the PDCs as they moved and interacted with the landscape. To dig even deeper into what made up the 2018 eruption deposits, scientists used scanning electron microscopy, or SEM, to zoom in at microscopic scale up to 50,000 times magnification. They analyzed 155 particles, looking at their shape, internal bubbles or vesicles, and surface texture. Most of the pyroclastic flow particles had low to moderate vesicularity, and many had no visible vesicles, possibly due to dust. Their shapes were mostly blocky and angular, and their surfaces were typically smooth with some rugged, fractured, or jagged features. When comparing fallout from the June 3, 2018 subplinian eruption to a previous event in 2017, the differences were striking. The 2018 fallout had larger and more vesicles, indicating more gas in the magma. Meanwhile, the 2017 particles had smoother, molten-looking surfaces, suggesting they cooled rapidly and came from a low-viscosity magma. These micro-level insights help link eruption style to particle formation, giving us clues about magma behavior and explosivity. The rock fragments inside the pyroclastic flows tells a powerful story. By analyzing particle textures and composition with SEM and microscopy, scientists were able to distinguish between juvenile materials, those formed during the current or recent eruptions, and accidental lithics, which were older rocks picked up during the flow. In the earlier PDC units from the June 3 eruption, we see a dominance of juvenile clasts, like black scoria and fresh glass, but as the day progressed, later flows, especially from 330 onward, show a shift toward older, reworked material, oxidized and altered glass from past eruptions. This suggests that early flows erupted fresh magma, while later flows were more destructive, pulling loose debris from previous deposits on the steep upper flanks. Scientists group the particles into three categories: juvenile, accidental, and free crystals. Interestingly, free crystals were consistently high across all samples, with the highest crystal content found in the tephra fallout from the subplinian phase. This evolving mixture of materials not only helps reconstruct the sequence of events, but also deepens our understanding of how PDCs gather and transport material during explosive eruptions. The June 3rd PDCs weren't just the result of one big collapse, but a series of sequential failures that grew more destructive over time. Early in the eruption, the summit explosions deposit hot, loose tephra along steep slopes. As the day progressed, this unstable material, along with layers built up from previous years, collapsed under its own weight, especially after being hit by ballistic debris. Scientists identified three major zones of collapse. T1, made of tephra from just hours before. T2, made of deposits from eruptions between 2015 and 2018. And T3, which included older, deeply buried materials. These collapses triggered PDCs at different stages, some small, some massive. As the PDCs raced downslope, they followed narrow ravines, which gave them speed and power. Some flows remained valley-confined, while others spilled out, especially when the channels filled up or narrowed. The critical moment came between 3:12 and 3:16 p.m. The first two PDC pulses filled the Las Lajas channel, but the third pulse breached the western bank, spilling into San Miguel de los Lotes. This was the deadliest moment of the eruption. Later flows followed this same path, reaching up to 9 kilometers. These flows behave like granular fluid avalanche, where particle interactions and gas expansion kept them moving. High temperatures and channel confinement boosted their reach, but once channels overflowed, they spread laterally and varied entire areas with massive and fast-moving ash and also rock. The 2018 eruption of Fuego was a turning point. Unlike past events, it occurred without much warning, reached peak intensity in just a few hours, and unleashed pyroclastic flows long after the main eruption column had subsided. What made it so deadly were two key factors: the rapid collapse of unstable material high on the volcano's southeast flank and the overspill of pyroclastic flows at 90-degree bend in the Las Lajas ravine. That overspill led straight to San Miguel de los Lotes. Since then, scientists have confirmed that pyroclastic material continues to accumulate in the same high-risk areas. Given the frequency of eruptions since 2015, there is a real concern that another major collapse and another overspill could happen again. In response, local authorities have taken major mitigation steps, rebuilding the Las Lajas Bridge, reinforcing the ravine at overspill Site 3, and excavating deposited materials. These efforts are meant to keep further flows confined. But the key going forward is proactive monitoring. High-resolution terrain models updated regularly, combined with mass flow simulations, can help predict where flows will go and when evacuations should happen. Timely data and community readiness could make the difference between disaster and safety in the next eruption. The 2018 eruption of Fuego was one of the deadliest in the volcano's history, largely due to how far and how fast the pyroclastic density currents traveled. These weren't just explosions. What made them so dangerous was the gravitational collapse of unstable material that had built up over years. Scientists classified the deposits into three types: valley-confined, overbank, and ash cloud surge layers. The sequence of collapses, called T1, T2, and T3, each unleashed a new pulse of pyroclastic flow. The most critical moment came when the first two flows rapidly filled the Las Lajas channel and the third one overspilled at a bend, flowing directly towards San Miguel de los Lotes. And this eruption taught us that even without major warning signs, structural instability and accumulated debris can trigger devastating flows. Understanding this process helps us better predict and prepare for future hazards. Thank you for listening. And again, I am Rose Manzanal, a third-year geological engineering student of Batangas State University.